All right, let's get right into it. So imagine a scientist creates a map. Maybe it's a map of a forest from a satellite. They face this huge fundamental question. How do you know if the map is any good? How do you actually measure if it's true? For decades, there's been a go-to answer for this. But as we're going to see, it might have been the wrong answer all along.
And that's really the core question, isn't it? It doesn't matter if you're mapping cities, tracking wildfires, or really classifying any kind of data. You need a solid, understandable way to score your work. You need a number that tells you straight up, how good is this map? Now, the most obvious way to do this is to just count up what you got right and turn it into a percentage. It's simple, everyone gets it. But for years and years, researchers, especially in fields like remote sensing, they've reached for a much more complicated and supposedly much more sophisticated tool. And that tool is the Kappa statistic. For the longest time, if you were trying to figure out how accurate your map was, you pretty much had to calculate Kappa. It was considered the gold standard, baked into all the major software and just a standard part of doing good science. So you have to ask, why? Why did Kappa become the king of accuracy? What was it supposed to be doing that a simple percent correct score couldn't? Well, Kappa came with this very, very clever-sounding promise. And listen, we're not talking about some obscure little formula here. As this quote from 2009 shows, Kappa was everywhere. It was deeply woven into the fabric of the science. It was the accepted way you proved your map was worth anything. Okay, so here's the big idea behind it. Kappa tries to be smarter than a simple accuracy score. It looks at all your correct answers, but then it subtracts the agreement you might have gotten just from sheer luck. You know, like if a monkey was just randomly guessing. The whole point was to isolate the actual skill of your model from random chance. But, and this is a big but, here's the twist. The very thing that made Kappa so popular, this whole idea of comparing it to random chance, is what a group of researchers now argue is its biggest, most fatal flaw. They're basically saying this idea has been leading science astray for years. And this slide just lays it out so perfectly. Kappa is built to answer the question, is my map better than a totally random one? But think about that. Is that really what a scientist needs to know? The authors of this paper say, no. A much more helpful question is, my map isn't perfect, so why is it wrong? What kind of mistakes am I making so I can actually fix them?
And they really don't pull any punches. They call it useless, misleading, and/or flawed. And it makes sense, right? Comparing your carefully built scientific model to a random baseline, it's just not that useful. I mean, when is your alternative method ever going to be complete and utter randomness? The goal isn't just to be better than chaos. It's to understand your errors and get better.
Okay, so if Kappa's the problem, what's the solution? Well, this is where it gets really elegant. The paper proposes this brilliantly simple idea. Instead of one confusing number, let's break down every single error into just two basic types. First up, we have what's called quantity disagreement. This is the how much error. The ink analogy here is perfect. Let's say the real world has 30% forest, but your map says it's only 10%. You have a quantity error. You simply used the wrong amount of forest-colored ink when you made your map. The totals are off. And the second type is allocation disagreement. This is the where error. So in this case, maybe you got the total amount of forest right. Your map is 30% forest, just like the real world. But you put that forest in all the wrong places. You used the right amount of ink, but you splashed it in the wrong spots. I know this might still sound a little bit abstract, so let's make it crystal clear. We're going to use a super simple 9-pixel grid from the paper to show you exactly how these two types of errors look in practice. Okay, so here's our reference map. This is what we're calling the truth. It's a simple little world with 9 pixels. 6 of them are white and 3 are black. This is the correct answer we're aiming for. Now, take a look at this map. See the problem? It only has 1 black pixel when it's supposed to have 3. The total amount is wrong. This is a pure quantity disagreement. Simple as that. We just didn't use enough of the black ink. And now, look at this one. We've got exactly 3 black pixels. So the quantity is perfect. But if you compare it to our truth map, they're all in the wrong spots. This is a pure allocation disagreement. The right amount of ink, just painted in the wrong places. So this is the big takeaway, this simple, beautiful equation. Any error in any map, no matter how complex, is just the sum of these two things. The how much part you got wrong and the where part you got wrong. That's it. No weird ratios, no confusing comparisons to random chance. It's just clean. So what? Why does this matter?
Well, let's look at why this isn't just some neat little academic exercise. This approach actually gives scientists something they can use to make their work way, way better. Okay, now check out this chart. This is where the light bulb really goes on. These are two real-world studies. The old Kappa score gave them almost the same grade, 0.69 and 0.65. You'd look at that and think, yeah, they're about the same quality. But when you break down the error our way, you see a completely different story. The first study has way more total error, but most of it is allocation error, putting stuff in the wrong places. The second study has less error overall. Kappa completely hides this crucial difference. It's giving you one blurry number when you need to see the two clear parts of the problem. And that's exactly why this matters so much. It's all about getting actionable feedback. If you have a big quantity error, you know there's a problem with how your model is counting the totals of things. If you have a big allocation error, you know the problem is with your model's spatial logic, its sense of geography. You're not just staring at a single, confusing score anymore. You now have a diagnosis. You have a clear path to go back and actually fix your model. And that really brings us to the final thought here. For so long, a really complex statistic was the standard because it felt more, scientific, more rigorous. But what this simpler idea shows us is that maybe true rigor isn't about complexity at all. Maybe it's about clarity. When we're trying to measure and understand our world, maybe the best tools aren't the most complicated ones, but the ones that give us the clearest, most direct, and most useful picture of where we've gone wrong.